All right, this is our first lesson, section 7.1, trigonometric identities. Hopefully some of these identities look familiar, as in you have seen them last year. So the top part of your notes sheet that you have the fundamental identities box, here you should know these identities very well, as many of them are also deck questions. So the first thing we're going to do is we're going to first identify the difference between what an equation and what an identity is. So we're going to go through each of these examples and say whether or not it's an equation or an identity. Remember, to be an identity, it means that both sides equal the same exact thing. To be an equation, you could actually take that situation and actually solve it for x. So the first one for A, we have 2x plus x equals 2x plus 2, which we could actually solve that. You could get the left side to be 3x, and then 3x equals 2x plus 2. We could actually solve that one. So this one is an equation. For part B, we have 2x plus x, and the other side is 3x. Well, 2x plus x is 3x, so this one is identity. For C, we have x plus 1 on one side and 2x plus 2 on the other. You can move your x's over, move your values over, and this one is an equation. Part D, if you distribute that 2 in, then the two sides equal each other, making it an identity. E, if you actually look above, actually it's not above, I was just kidding. E is an identity. It's the sine 2x identity, which we do get to the next section, I believe, or maybe the section after that. F, if you look at that, we have 2 sine squared 2x plus 2 cosine squared 2x equals 2. If you factor a 2 out of there, then you get the trig identity that's up above. So this one's an identity. And lastly, you have 2 sine squared 2x equals 1. You could actually move your 2 over, solve for sine, then solve for x. And this one's an equation. Using our trig identities, we're going to start simplifying. So you might want to go ahead and star your notes here, as trig identities do show up on your final exam at the end of the year. Well, when you have two parentheses together, what's the first thing we do? We're going to FOIL. So 1 times secant y, we get secant y. 1 times tan y, negative tan y. Sine y times secant y is sine secant y. And then last, sine y times negative tan y, negative sine tan y. I'm going to have to erase some of that so I can do B. There are some things that we can change, such as the sine and the secant and things like that. We can get them so that they are all the same denominator. Secant is 1 over cosine. Tan is sine over cosine. Then we have times sine y. Oh, oops, no we don't. Sorry, plus sign there. Plus sine y times secant 1 over cosine y. Minus, we have sine y times sine y over cosine y. Good so far? Well, sine y times 1 over cosine y, this part right here, is the same thing as the one before. So these cancel. Then we have 1 minus cosine, 1 over cosine minus sine squared over cosine. And 1 minus sine squared, well, that's just the reverse of a trig identity up above. 1 minus sine squared y is equal to cosine squared y over cosine y. And cosine squared y over cosine y, they each have a cosine, so this will reduce to cosine y. Very good. I will switch colors and I will actually start this next one. We can actually separate our parenthesis or our fraction. Getting to sine theta over cotan theta plus cotan theta cosine theta over cotan theta. Well, in the first one, sine over cotan. Cotan can be changed to cosine over sine. Those are the same thing. They're equal. You can see it up in the box above. And if you are dividing a fraction, it's the same thing as multiplying by the reciprocal. So this first fraction becomes sine theta times sine theta over cosine theta plus, well, here our cotans cancel and we're just left with cosine theta. To make it one fraction, the second piece needs the cosine. So we're going to multiply the second part by cosine over cosine. So we get common denominators. Let me erase some of this. So we get sine squared theta over cosine theta plus cosine squared theta over cosine theta. And sine squared plus cosine squared on top is equal to 1. 1 over cosine theta. 1 over cosine theta is equal to secant theta. All right, and the last one on your front page says, given that sine squared and cosine squared equals 1, that's one of the trig identities from above, find an identity for tan squared x plus 1 and show that it's valid. Well, tan squared x plus 1. We can change tan squared x to sine squared x over cosine squared x. And if we have a denominator of a cosine squared, well then let's change the 1 to cosine squared x over cosine squared x. Well, the numerator, sine squared plus cosine squared, is equal to 1. That's why they give us that part in the beginning. And 1 over cosine squared, just like the problem before, is secant, but this time it's secant squared x. On to the back. The top part talks about guidelines for proving trig identities. You always start with one side. You want to start the side that's the hardest, the one that has the most complicated stuff. So usually fractions, things that have more than like 3 different identities, things that you could maybe factor out, anything that's harder, that seems harder, that's the side to start with. Then we start bringing into our identities that we have, and then if you can't figure anything out, convert everything back to sines and cosines, and that should be able to do something for you. The next thing is we're going to decide if whether things are reversible or irreversible. If we have an x squared, what do you do to unsquare a squared? Well, you take the square root. But remember that if you take the square root of something, it's positive and it's negative form. So since there are 2 things that it could possibly be, this is irreversible. For part B, to get rid of a cubed root, or to get rid of to the third power, you take the cube root, which is actually either a positive or a negative. That one only has one answer, so this one is reversible. C is the cubed root of x. To get rid of the cubed root, you would cube it, which there is only one answer, so this one is reversible. If we have x plus c, to get rid of to do the opposite, you would do x minus c, so this is reversible. And if we have c over x, to get rid of the c, you would divide it by c. But remember that c cannot equal 0 because you cannot divide by 0, so this is also reversible. Proving trig identities. We're actually not going to do B, so you could go ahead and cross that one off. Well, let's start with A. A says cosine x times tan x equals sine x. Okay. Well, looking at this, which side harder? Well, the left side is harder. It's got 2 terms instead of, or 2 identities, or 2 functions instead of 1. Can't do anything with cosine, but tan I can change to sine over cosine. Let me write that sine a little bit better. Well, if I have a cosine in the numerator, cosine in the denominator, those can cancel, leaving me with sine x. One side equals the other side, and there it's an identity. Moving on to C. we have sine cubed u on top over 1 plus cosine u equal to sine u, and then in parentheses 1 minus cosine u. Uh-oh. Oh, I kind of fit it. While looking at the two, fractions are definitely the harder side. So what I'm going to do is I'm going to take sine cubed u. And the bottom's already a cosine, so if there's some way I can change a sine into a cosine, I want to do that. I can't change a sine to the third, but I can change a sine squared. So I'm going to rewrite it as sine squared u times sine u, and then leave my denominator. Well, sine squared u is equal to 1 minus cosine squared u. Oops, that's a sine. Well, 1 minus cosine squared u, isn't that a difference of two perfect squares, right? So I'll double bubble that. 1 plus cosine u, 1 minus cosine u. There's still a sine u at the end. The bottom is 1 plus cosine u. 1 plus cosine u's go away, leaving me with sine u parentheses 1 minus cosine u. Matches the other side. All right. D. We have tan theta plus cotan theta equals secant theta cosecant theta. Draw my line down. Which side is harder? Well, they both each have two functions on each side, but one is a plus, one is a minus. The one side with the plus is definitely going to be the one that has the harder side. I can change tan into sine over cosine. I can change cotan to cosine over sine. Now they are adding. They do not have common denominators, so you cannot go ahead and just combine them. But to combine them, we want a common denominator of sine cosine. This first fraction is missing the sine part, so we're going to times it by sine over sine. The second fraction is missing the cosine over cosine part, so that's what we'll do. So we get sine squared theta on one side, cosine squared theta on the other. Sine squared plus cosine squared is a trig identity. It's equal to 1, so you equal it to 1. So we have sine theta, cosine theta in the denominator still. Well, 1 over sine theta is equal to cosecant theta. 1, I could add a 1 there. 1 over cosine is equal to secant theta. It matches the other side. And then last one for today's notes says it's given us square root of 1 plus x squared. And x, they say, is equal to tan theta. Well, we're going to plug tan theta in for x then. So tan theta goes in for x, so now we have 1 plus tan squared theta. 1 plus tan squared theta, that's an identity. It's equal to secant squared theta. And the square root of secant squared theta is secant theta. All right, I hope this explains it. Make sure you ask questions the next day if you have any.